Thank you for your introduction. I am Matsuura. I am very happy to be able to talk to you today. Today I'd like to talk about interaction system, Scoopirit. At the beginning, I will introduce our system easily. Scoopirit displays mid-air image on real water surface, and user can scoop up the image at any horizontal position. And image can move 3D position like this. If the system changes the image position, user can scoop it. I'd like to start by talking about our motivation. Here, water surface is an important component for designing public spaces around the world. There are lots of artificial created water surface. The presence of water relaxes visitors to public spaces. Our aim is to create a system to make such a water surface more appealing. How can we make it? So we focused on introducing interactive visual expression to the water surface in public spaces. Now I'd like to introduce two works related to our purpose. First is water screen. Water screen is a thin film of water ejected from a pump, acting as a screen for projection. So the system can display images vertically standing on the water surface. However, the system sprays water around and prevents people from getting close to the screen. Therefore, the system is suitable for display, so not suitable for interaction. Second is aquatop display. Aquatop display is an interactive water display system that enables an image to be projected on a water surface. The user can manipulate the image with their hands with a depth sensor. The system uses a large amount of bath agent to whiten water. Therefore, the system is amazing, but not suitable for public spaces. Our purpose is introducing interactive visual expression to the water surface in public spaces. Therefore, we defined three requirements for the purpose. First, no water processing. Second, no device wearing. Finally, geometrical consistency. The first requirement is that the introduction of the system does not change the characteristics of water in the public spaces. While circulating the water in the public space for cleanliness, it is difficult to keep it quite cloudy. The second requirement is that the multiple users can share experience without needing to wear a device, because public space is a place where many people gather, from children to elderly people. The third requirement is that the system always maintains a 3D positional relationship between the real space and the virtual image. And the three-dimensional in the left figure, a computer graphics fish that should be underwater is projected flat on a water surface. In the right figure, a computer graphics fish that should be underwater is correctly present under the water surface. By satisfying this requirement, many people in public spaces can easily understand the relationship between the real space and the image. To satisfy the three requirements, we explored another methods. And we focused on mid-air imaging technique Mid-air image is an image located in mid-air. User can see mid-air images without wearing special eyeglasses or like. One of them, Mario system, enables users to interact with mid-air images on the real table using real objects. The system satisfies two requirements. The requirements are no device wearing and geometrical consistency. So we decided to use mid-air imaging technique for our purpose. And there are several mid-air imaging techniques such as MMAPS, DCRA, RMA, and AIRR. And there is an optical system that displays underwater image using AIRR. In this research, we use micromirror array plates to focus on interaction. MMAPS consists of two layers of micromirrors, which are orthogonal to each other. The incident light reflected once in each layer of the MMAPS. So the MMAPS can form a mid-air image at the position that is plane symmetrical to the MMAPS. Scoopirit displays mid-air image on water and underwater. And the image can move three-dimensionally. And users can scoop up the image with their hands at any horizontal position. And the system satisfies three requirements that I mentioned before. Scoopirit is roughly divided into two subsystems: optical subsystem and feedback subsystem. The optical subsystem extends the previous system using a reflective surface and enables the displaying of a mid-air image on a table surface. The subsystem consists of a display D and MMAPS and rubber film and water tank. The user can see the mid-air image reflected on the water surface like this. And the visible area is green colored area in figure. To form a mid-air image under and on the water, the images requires two different optical passes. First, to form the image underwater, MMAPS reflects light from a light source at D1 located above the water level and forms mid-air image at I1 dash. And the virtual image I1 of the at I1 dash reflected on the water surface is the underwater image that user can see. Second, to form the image on water surface, the water surface forms the mid-air image at I2 on the water surface with light reflected from the MMAPS from another light source at D2 located below the water level. Since the rubber film blocks the light from light source display, which goes straight to the user without being reflected from the MMAPS, the user cannot recognize the space in behind of the MMAPS. If there is no rubber film, the user can see a display behind the MMAPS. It is not attractive, so we use rubber film. And the image can move in depth direction using linear actuator. This is a video when the fairy ran with full power and approached me. It's very cute. And figure shows implemented optical subsystems. Since the viewing angle of the mid-air image is narrow, so it is necessary to design the interaction area. So we made model of interaction area. The area is an area that the image can move and the user can scoop. With the model, you can design the scooping distance and image moving range. And I made a model of eyebox. Eyebox means the movable area of user's eyes. with this model, you can design the viewable point. You can choose between two models depending on the application. Now I'd like to talk about feedback subsystem. The role of the subsystem is to control the position of the light source according to the height of the water surface. As the position of the light source is lower, the position of media image is higher. Then let's consider the case where the height of the water surface rises without changing the position of the light source. Then the position of the media image relative to the water surface rises more than before, like this. Therefore, the user cannot scoop the image with this way. To solve this problem, it's necessary to raise the position of the light source by same amount as the increase of the height of water surface. Therefore, the feedback subsystem measures the height of hands with an RGB-D camera. We install the camera in vertically downward direction. The PC controls the light source position according to height information, like this. And there are two ways to measure the reflecting surface. One is ultrasonic sensor, and another is RGB-D camera. But ultrasonic can measure only one point directly under the sensor. So we use an RGB-D camera. RGB-D camera can measure any horizontal positions. But RGB-D camera cannot measure the height of the water surface. It measures the bottom of scooping hand. So we showed that if the system adds offset value to the RGB-D camera's value, the values of ultrasonic and RGB-D camera will be almost same. So we need to find a proper offset. To decide proper offset value, we performed an experiment. We wondered if there is some relationship between the offset and the hand length. 8 participants perform the following procedures. The participants adjust the vertical position of the image to a point that they can recognize the image as floating on the water surface using a keyboard. Next, we set the offset value randomly. Next, the participants scoop the images as they want times and adjust the offset value until convincing. After that, I recorded the adjusted offset value, and I measured the hand length, eye position, and scoop the distance. As a result, there is no correlation between all parameters. So we showed that it is difficult for participants to distinguish between underwater image and floating image. And we decided to use average of the offset values. This movie shows the scooping interaction when using the average offset value. So user can scoop up the image. In conclusion, today we introduce our system, Scoopirit. Scoopirit can display media image on water surface and underwater image. The image can move three-dimensionally, and the user can scoop up the image at any horizontal position. And we model the interaction area and eye box, and we explore the method to decide offset value for tracking. Thank you for listening.
We have time for some questions, so please walk up to the microphone, state your affiliation and name. So I'll start with a question. So I tried your demo yesterday, as you know, and I asked you the question, what were the applications, right? You mentioned those requirements that you had, but so basically you seem to have just one simple interaction. So how you envisage that to be implemented maybe in, I don't know, you showed some fountains at the beginning, or like aquatop, the bathtub. So could you tell a little bit about the applications?
You mean other applications?
Yeah, so how do you expect people to use that? Is it just for like a playful interaction, or is it something people can, is it something useful also?
Yes. For example, we think that displaying on wet asphalt like this. Because when asphalt is wet, reflectance of asphalt is rises. And in another application, we consider.
So what does the user do then? It's just like a small puddle, right? Is the user meant to scoop up the frog? Or?
When we show in this way, user cannot scoop. Yes.
Any questions from the audience? So just to follow up on what I was saying, so you have like aquatop. You showed that was like a very popular system that was shown a couple of years ago, and you have a big, like a little bit complex apparatus to project on this basin. Do you think you could have that in a bathroom? With aquatop is like a larger water surface. Do you think this your system would scale to larger water surfaces?
Scary. You mean
like
scaling?
in I have a larger bathtub in my bathroom. Do you think you could design your system also for bathrooms and bathtubs?
I think it is okay. The system can display on bathroom water surface. It's okay.
But so the projector and everything that's required, does that scale up to the size of a bathtub?
About size?
Yeah, I mean you have like you have some minor adjustments that you make to so that the projection is able to sort of target the basin, and then the interaction spaces seems to be a little bit limited.
Yes, it is limited, but image size of image depends on MMAPS size and image position. So if we want to display the big size image, we should use big size of MMAPS. It's okay.
Okay, so if there's no questions from the audience, let's thank our speaker again. Thank you.